We've got a special uh, kind of extended play episode today because we're going to hear from three of our piloting teams about actual practical issues they encountered in doing these pilots. And so I'm going to share my screen and we will get things kicked off. Welcome, everybody. All right. Jim, can you see my screen?
Good.
Thank you. All right. Well, everybody, first of all, welcome to this webinar series. A little housekeeping. We record these meetings, this one in particular, because we know many of you are actually listening to this recorded, partly because our goal today is not just share some of the successes we've had in our piloting process so far, but to give practical advice to teams and researchers who are contemplating building and operating pilots for future research projects, including upcoming NAWI funding opportunities. So this is recorded. We have you muted during the duration of the presentation. However, at the end, we will open it up for questions. We recommend if questions come to you, put them in the chat right now or as you are thinking about them, and then we will unmute you and you can ask your question directly. And then for those of you who are, sort of coming in from afar and aren't part of the NAWI community already, we always recommend that you join our LinkedIn community because this is where we post information on our upcoming webinars. Another little element I'd like to do right now, as I said, chat is a great place for you to put your questions. Just open up the chat window and put them in as we go along. And then the other thing I'd like you all to do today is go to your little video, your thumbnail, and put your cursor on the thumbnail, and you will see a little box in the upper right-hand corner with three dots. And that, when you press on that, you will open up a window that will allow you to rename. So what we'd like you to do is just add your affiliation. So I'm going to add NAWI. And if you can do that, then everybody else can see who's here, where you're coming from, et cetera, et cetera. So Ali and Kevin and Russell, if you could do that, that'd be awesome. Jun Lee is here. This is great. We've got a great group of people here today. Wei Tong, Thomas Price, Carl Longley over there in Fresno. Good to see you, Carl. All right. So, seriously, follow us on LinkedIn. This is the best way for you to keep track of us and our program and our upcoming webinars. And then we will be posting this recording to join all the other webinar recordings on our NAWI YouTube channel. So if you haven't checked this out yet, take a snap of this QR code and check it out. This is where all of our content is ending up. And it's got a great resource for all of you. Now, I just want to tell you that we are on Thursday, September 17th. This is about 1 month from tomorrow. We're going to have Dr. Pei Xu from New Mexico State University giving us a presentation on some of her work surrounding the NAWI Project 3.15. Many of you know Pei and her team have been pioneering advanced electrodialysis techniques for not just separating brine from fresh water, but also transforming that brine into different chemicals and valuable constituents. And she's going to go into depth, not just about Project 3.15, but also some of the other exciting work that's going on, including at the Blue Brine facility just outside the fence in the El Paso Cape Bailey Hutchinson inland desalination plant. All right. Just before we begin, just to remind everybody, these are open webinars, but our views and information is not representative of NAWI or its members, organizations. But we do this as a public service to help everybody understand the forefront of water technology today. So with that, I am going to stop sharing, and we're going to go in the following order. We're going to have Jim and Logier and Laura Alvarez start with their presentation on their project. We're then going to go on to Lisa Tomenendal and Zahi Kath for DPR trailer and wrap up with the Trevi team talking about their project, which traveled several locations across California. So with that, Laura, why don't you get started and share your slides and tell us about the project. Thanks for coming.
All right. Hello, everyone. Can you hear me well?
Yeah,
And can
sound
you see
great.
the slides?
We do.
Perfect. All right, I'll let Jim Lisher to introduce our team
Sure.
and our project.
We'll talk about NAWI 3.19, reverse osmosis with virtual curtain to achieve minimal liquid discharge. Next slide. So our team consisted of myself, Laura, Michael Wong, also from Jacobs, and Grant Douglas down in Perth, Australia. He was really the brains behind and developer of the virtual curtain process we're going to talk about today. And Peizu served as our co-PI and managed all the bench scale testing work that preceded the pilot testing. And then we had a number of industrial partners that participated. And most importantly, Bureau Reclamation, as we'll talk about more, because that's where we conducted our work and who worked with us on that project. Next slide. So why does RO concentrate minimization matter? Well, conventional RO technologies that we use typically for brackish water treatment are limited in recovery to 85%. So this gives us a fair bit of concentrate we have to dispose of. And for inland water, inland sites where a lot of brackish groundwater exists, that really constrains the cost of the overall project, particularly the cost of concentrate disposal, because we have to use evaporation ponds or thermal systems like brine concentrators, and those are quite expensive. And evaporation ponds also sometimes create environmental issues associated with their siting and operation. So mineral scaling is generally the problem we have in trying to push RO recoveries, silica in particular, but also calcium carbonate and sulfate salts. And so what we want to do here with our project is try to reduce that scaling potential to allow us to use RO to get to a maximum recovery. So when we try to go to minimal liquid discharge or zero liquid discharge, we can push to a higher recovery, a higher TDS in our RO concentrate, and therefore reduce how much thermal or evaporation ponds we need in order to get to ZLD. And that really reduces the cost and increases the efficiency and ability to actually treat brackish groundwater effectively. Next slide. So we have two means by which we can reduce the scaling potential of RO concentrate. One is conventional chemical precipitation, where we operate at relatively high pHs, 11 to 11.5, in a solids contact reactor, which generally has a long residence time and therefore a large footprint, and obviously requires chemicals to get to those pHs and to precipitate our scaling ions. So in this project, we looked at a different approach called the virtual curtain process, where we actually form a compound called hydrotalcite in situ. And we do that at pH 9.5, so much lower pH, lower chemical use. Also, the reaction kinetics are very quick. We form hydrotalcite within minutes, and that allows us to reduce the footprint and time we need to take that reaction to completion before we can then further treat that with another RO step. Next slide. So our project goals were to validate the integrated virtual curtain process for treatment of RO concentrates, two different sources, a brackish groundwater supply that had been through RO process, and then agricultural drainage water under pilot scale conditions. And the idea here was to reduce the scaling potential of the concentrate produced from these two sources, targeting our magnesium and silica removal as well as calcium removal. And by doing this, allowing us to then retreat that concentrate and get to a recovery of RO up around 95%. That was our goal, allowing us essentially to triple the brine TDS in that RO concentrate and also reduce the volume, most importantly, at the end of the day. So then we wanted to quantify the economic benefits of the hydrotalcite-based pretreatment compared to the conventional process I showed earlier, and then obviously look at the sustainability benefits we might be able to derive from the formation of the hydrotalcite solids and improve the operational efficiency of the overall process. Next slide. So we did this testing at the Water Quality Improvement Center out in Yuma, Arizona. Why did we do it here? First of all, they have expert engineering and technical staff. They've been operating this facility for many years. They operate that facility 24 hours a day, 7 days a week, which means we can run our pilot continuously if needed. They also have existing pilot scale infrastructure in place. So they're used to dealing with pilot systems. And so we developed a relationship with the Bureau of Reclamation, who operates that facility along with their contract staff to do that. You can see a picture of the Water Quality Improvement Center here, co-located with the human desalting plant. And then David Guerrero served as our coordinator on the engineering side. Renee Morales was the manager superintendent of operations of the facility that we were pilot testing. Next slide. And so these two streams that we tested were available at the Water Quality Improvement Center. The first was agricultural drainage water that had been through an RO process after pretreatment, as shown here. And that gave us one source, but it was a source that was rather different in the sense that it had been softened already, and the pH that we received that concentrate at was around 5.5 to 6. So a very different kind of brackish groundwater supply for treatment. The second supply, more typical, was a brackish groundwater that was produced from a well that's located next to the Water Quality Improvement Center. There we put that through a typical pretreatment system of cartridge filtration, anti-scale addition, and then operated a pilot scale two-stage RO system to produce the concentrate for the virtual curtain process. The pictures are shown here of those facilities. Next slide. So I'm going to turn this now over to Laura, who's going to take us through the process we did, the testing results, and also obviously the lessons learned from those results and testing.
Thank you, Jem. On the screen, you can see the initial process flow diagram that we had at the proposal stage, only really including the major unit processes that were included in the pilot. But by the time we started construction, we already had put a lot more details into the page, and you can see the process flow diagram had evolved. Normally, we start with either agricultural drainage water RO concentrate or concentrate from brackish groundwater treatment. So the concentrates are treated using lanthanum chloride, magnesium hydroxide, sodium aluminate, and sodium hydroxide. Those were the chemicals that were initially selected for the virtual curtain process. The reaction takes place within a reaction tank, and the solids that are formed are separated using ceramic membrane filtration. During design, we also identified the need to include acidification in order to handle our first operational challenge, which was residual aluminum from the dosing of sodium aluminate upstream. So we included acidification and cartridge filtration to handle that excess aluminum and remove it as aluminum hydroxides ahead of our reverse osmosis unit. Lanthanum chloride during preliminary testing was identified to no longer be required as part of our treatment train because of changes that happened upstream of our pilot, so we removed it from the train. We also noticed that the external water sources that we were using to backwash the ceramic membrane filtration were actually resulting in a lot of fluctuations downstream in the acidification step, so we needed to make some modifications. And also we noticed that cartridge filters were plugging relatively quickly with the aluminum hydroxide, so we needed to find an alternative. As we tried different things at the pilot scale and during our testing, we landed on this final process flow diagram that you see on the screen. No longer having lanthanum chloride in our chemical treatment, we also repiped our backwash tank to now work as a backwash and filtrate tank, effectively eliminating those fluctuations we were seeing with the acidification step. And then finally, we phased away from cartridge filters and we move on to use ultrafiltration instead. So we translated all those concepts from the process flow diagrams into these construction plans that you see on the screen. We prepared these drawings prior to our first pre-construction meeting with the Bureau of Reclamation staff. And the idea was to communicate our design intent and then kind of put systems together that we were bringing to the pilot for this project, as well as using a lot of the equipment that they had on site. And we also relied a lot on their expertise to build the system and then operating in a way that was practical for them. So we involved them early in these discussions in order to have a product that they were happy with at the end of the day and that we were all happy with. So the final product is what you can see on the screen. We had this pilot inside of the Water Quality Improvement Center at one of the many test bays they have on site. They can actually have multiple test pilots going on at the same time. So something really useful. One of the units that we brought to site was the ceramic membrane filtration unit provided to us by Serafiltech, which is one of our industrial partners. This is the unit that filters the solids that are produced from the virtual curtain process, and then the filtrate from that unit is acidified and then filtered with the ultrafiltration unit in order to eliminate or remove that excess aluminum ahead of our seawater RO unit. This unit was specifically designed for this project by Jacobs and built by AMI. So now that you have a bit of a visual of what the pilot was, let's take a quick look at some of the results. So the idea was to apply the virtual curtain process to treat brackish groundwater or concentrate. In this case, these results correspond to the treatment of brackish groundwater RO. And the idea was to decrease the scaling potential of the water. So we achieved around 95% removal of silica, 75% removal of calcium, and 31% removal of magnesium. Along with that, we also were able to decrease the concentration of other scaling constituents such as barium, strontium fluoride, and orthophosphate. That alone enabled us then to increase our water recovery with our subsequent seawater RO treatment up to 95% without any signs of scaling. For comparison, again, without any chemical treatment, you could expect to hit between 70 and 80% recovery before you see scaling. So the fact that we were able to increase our recovery up to 95% was a major win for our project. Now that you know the wins, let's take a quick look at another one of our operational challenge. Here, we had also a lot of the accumulation of the HTC solids from the virtual curtain process that were accumulating in the piping, injection systems, and ancillary equipment ahead of our ceramic membrane filtration unit. The pictures that you see on the screen are actually after several months of using the pilot without any treatment and cleaning. This was easily remedied using citric acid for cleaning, but this experience definitely gave us a lot of insight into the chemical treatment and the chemical cleaning that was required, as well as maintenance for future pilots and full-scale applications of this process. So overall, the system performance was actually limited by HTC solids accumulation instead of membrane fouling or scaling. So after we finished the pilot, that gave us a bit of an idea of how to solve this issue. And at a conceptual level, we identified that potentially using a solids contact clarifier to provide a dedicated system for solids reaction and settling could be a way for us to streamline the process, eliminating a filtration step, and also handle that issue of the solids accumulation. Again, from a conceptual level, we saw that the virtual curtain process coupled with the solids contact clarifier was able to achieve around 31% reduction in life cycle cost in comparison to conventional chemical precipitation. So overall, the idea here is that not only does the virtual curtain process work really well to remove the scalings, but when paired with the right treatment train, it can actually provide some economic advantages. So something to keep in mind for future testing. From our pilot, we have a couple lessons that we learned. Number one, design for solids, not just for water, specifically in the case of processes like ours that we are purposefully introducing solids into the treatment train. So make sure that you design to maintain appropriate pipe velocities and eliminate dead zones. Also, design for cleaning from day one. Consider the inclusion of redundant equipment, spare piping, where solids are expected to build up. Also, when possible, inspect equipment after prolonged operating time, not just when it starts to make noises or when you start seeing failure. Make sure that you incorporate that as part of your regular maintenance and cleaning schedule so that you can change those schedules as needed based on your operation. Also, expect the process to change and make sure that you build flexibility into the piping, controls, and operations so that you can handle those changes. And automate when possible. For us specifically, pH control and chemical dosing were significant and very important parts of our treatment train. So they actually required a lot of operator attention. So when possible, integrate PLC controls such as feedback loops so that it can make it a lot easier for the operations team. And finally, but not least important, it is very, very essential to invest in operator training and maintain constant communication. I think this is key for any pilot, independent of the technology that you're testing. Overall, from our pilot, something that worked really well was the process itself. The virtual curtain process applied to the treatment of brackish groundwater RO concentrates was able to reduce silica by more than 95%, along with other scaling constituents. That allowed us to increase our water recovery up to 95% and achieve an overall system recovery of about 98.5%. Something else that worked really well was the fact that we're working with the best of the best at the Bureau of Reclamation Staff Water Quality Improvement Center. We had strong operator engagement, practical expertise, and creative problem solving that then enabled our pilot to stay afloat despite of the challenges that we faced with solids accumulation and aluminum management. Something that we'll definitely do differently would be automate critical control points when possible, and we'll definitely carry these lessons forward to our next type of testing in the future. With that, I want to thank you all for your attention, all our partners, and we'll be happy to take questions at the end of the session. So thank you all.
Great. Thank you, Laura. Fantastic. Now we're going to hold questions because we're going to roll through all three presentations first. So we'd like to now invite Lisa and Zahi to get your slides set up and join us. And again, as you have questions, put them into the chat. We will unmute you at the end, and you can ask your questions of the pilot teams, etc. So, all right, Lisa and Zahi, we see your slides. Looking good.
Cool. Thank you, everybody. You can hear me, right?
Yep.
So I'll start and then let Lisa. We're presenting lessons from NAWI 3.20 DPR in California. And I'll start with a few lessons learned from past pilot, because many of you who knows our operation at Colorado School of Mines, we have done many pilots for many years of both wastewater and desalination. I'll then launch the information about the direct potable reuse mobile lab, lesson learned from the recent piloting in California, the challenges, the solutions, and key takeaways. So I want to start with a pilot that we did 2 years ago in the summer of 2024 in Texas, operating a large low salt rejection RO system for high recovery of water from oil and gas wastewater, treating water that's more than 100,000 milligram per liter. It was a close collaboration, of course, with industry there. As you can see, we deployed in a place called Orla, Texas, middle of nowhere, really difficult to operate from logistical standpoint. We were, on the left side of the junction here. We also operated, if you can see on the top here, irrigation plot where we used our water and local water to compare irrigation. We learned many important lessons from that. First, this is the water that we had to treat. So pre-treatment was very, very critical. And bringing water in and out for these capacities of pilot system is not simple. Then we built the system with industrial SCADA system. And for experimental work, I would recommend to work with experimental SCADA systems and not with systems that are built more rigidly to control a water treatment plant. Of course, we operated many months, 24/7, collaboration with the partners, very important. And what we learned mainly from the design of the system is that we needed more robust sensors, especially flow meter, to deal with hypersaline and difficult water to treat. And this is a picture of the entire deployment with the systems, with the 10,000-gallon tanks, beautiful place. The next one is what provided us the inspiration to do the direct potable reuse. This is a pilot that we had on campus at School of Mines for 18 years, operating 24/7, great collaboration with Aquarobic Systems. This is a sequencing batch reactor combined with membrane bioreactor, treating student wastewater and enabling, as you can see here, many types of research question to do on your own wastewater. We learned an important lesson from operating 24/7 for many years. One of them, the diversion. So we diverted raw wastewater from student housing to the site. Don't do it with 4-inch pipes. Do it with something larger than that. Winterization. Working in Colorado, you cannot let a pipe freeze. And simple solutions, like you see on the left side, didn't work. So luckily, we had the funding to build something more durable around the system. Keeping bugs alive in a small sewer shed is not simple because every discharge of bad water can impact. And then as the system gets old, things change. Its maintenance is more complicated, replacement is more complicated. So with this experience, we decided to dive into direct potable reuse with the intention that we'll have again a durable system that worked for many years, but mobile. So we can take it from one place to another. And we started in 21 in Colorado Springs. The unique thing about it, we incorporated more than 9 processes in one small footprint. So operating this is more complicated than piloting just one process or 2 processes. So it's a highly monitored system with a lot of sensors, 2 SCADA systems, and systems that produce more than 1.5 million data points per day. So as you can see, we took it to many places, and we've been operating it continuously since 2021. Lately in Lakewood, in Redwood City in California, and we are back now in Colorado. And I'll let Lisa tell us a little bit about the experience that she had operating the system in California and some stuff in Colorado.
Hey everybody, let's get this next slide is not clicking. There we go. So for DPR to work, one of the key things that we have found over the years is the feed water quality must be conditioned. So some challenges and limitations and that is involved here is coordinating with the wastewater treatment plant, collecting a lot of samples, specifically after each unit process, the cost of analysis, and a good example on the bottom here, we do have a recently published paper that talks about our experience during our first year of deployment. And you can always look at that at another time. So our trailer incorporates, like Zahi said, more than 9 processes. So this is kind of our standard schematic inside the trailer. Has a lot of flexibility here. Things that we can do and manipulate are the configuration of our absorption columns, whether that's operating in series or parallel. We can also look at different absorbent types. We can also look at an RO versus a non-RO treatment train, as well as comparing different UVs. We have a UV LED as well as our standard low pressure lamps. Some other flexibilities we can do is we can bypass systems. We can also turn systems on or off, and we can redirect, here specifically, the RO waste stream can either go back into the feed to go downstream through the absorption columns, or we can just send it to waste. On top of that, we have a lot of water quality sensors and analyzers to help keep track of just how the water quality improves throughout the treatment train. Some original design challenges from when this was built, it was built in 2021, figuring out how to maximize our capacity in a small footprint, considerations like height limitations, flow and pressure balancing between active and passive processes, as well as maximizing our data collection with a small number, with the sensors that we were provided at the time, including the use of automated feeding manifolds. And I will touch back on the feeding manifolds later. So in preparation for our California deployment, as Zahi mentioned, the DPR has visited multiple locations, different wastewater plants in the Colorado or Denver area. While we were at Denver Metro a few years back, it was our first experience dealing with secondary effluent, which is much higher in solids than our tertiary that we've used to receiving. So we found some new challenges with this, including our pre-filter getting clogged. So to kind of overcome this issue, we installed an additional pre-filter followed by a storage tank to make sure that when these filters backwash themselves, we're not sacrificing the pressure needed to continue operation. This was also the first time in 3 years of continuous operation that we found benefit in installing an alarm for a system shutdown in the event that there's a severe clog that impacts flow or whatever other issue may impact the continuous operation. At a secondary or another location, we went to South Platte Renew in Colorado and also found other sources of issues impacting our pressure that feeds the trailer. We installed this bladder tank. You can see on the right, we circled it. And And that tank just helped ensure constant pressure, even if the water coming from the wastewater plant had interruptions in that pressure. Moving more towards our deployment in California, our goals here were largely to simultaneously test DPR and IPR treatment configurations. In California, they have different regulations for the water quality coming out of their wastewater plants, specifically nitrogen removal. So things we were wanting to be able to accomplish were maintaining a high water quality effluent from the trailer, finding greater than 95% removal of ammonia levels that were coming in greater than 40 milligrams per liter, keeping nitrate below 10, and also really focusing on ways to develop low-cost, scalable solutions when comparing, like I said, DPR versus IPR, as well as an RO versus a non-RO treatment train. So the water quality, this is some data we got preliminarily before we traveled to California. And we knew based on this data and communicating with the wastewater plant that there were high levels of solids, as well as nitrogen and phosphorus, greater than 40 milligrams per liter of ammonia here, greater than 10 milligrams per liter of phosphorus. So we knew that those can be challenging things to remove, and wanted to do some prelim studies on how to tackle these constituents. And like I mentioned, we can do some non-RO versus RO comparisons. Some of these things can be removed with RO, but not necessarily through a non-RO train. On the right-hand side, so this is a kind of a graph of a lot of options we have for treatment train. And on the right is our advanced treatment. These are all options that we can explore using our DPR trailer, including treating through RO or bypassing RO. To handle some the ammonia removal that we knew we were going to encounter, we had some lab scale nitrification trickling filters, some biological active filters for denitrification, and we were able to achieve complete removal of ammonia in small batches. However, once we traveled to California, we found that the wastewater plant we were working with had already brought in a biological double efficiency pilot, this BDP. You can see it pictured. On the bottom photo, it's a good depiction of the BDP on the right and our trailer on the left. Unfortunately, it wasn't properly vetted, and as a result, we weren't able to achieve a stable removal of nitrogen or solids. This is just kind of a 4-month depiction of some of the data from that BDP, really just showing the fluctuations. We couldn't get that consistent removal of nitrogen or our solids here. So that became a big challenge for the duration of our deployment. In order to try to tackle some of the issues with our solids, while we initially implemented an additional pre-filter like we did at one of our Denver locations, the solids was too high, overwhelmed that additional filter. So we brought in instead a cloth media filter. I provided some data here to show, what that filter, what the water quality was coming in from a solid standpoint versus coming out of that. So it was much more helpful than the other pre-filter we had, but still, obviously, there's room for improvement. Moving into maybe more of a technical side, looking at some of the sensors and the water quality monitoring on the trailer. Some of the inline analyzers that we have in the trailer, a biotector for TOC and Amtax for ammonia, require special filters that also require special maintenance. They're kind of circled here on the right-hand side to make sure with smaller tubing, we're not clogging those expensive analyzers. We also have an ozone sensor on our trailer to keep track of how much ozone is actually being transferred into our water. And in the case of going to California, an air dryer was necessary due to the higher humidity that is there versus in Colorado. Something we found to be priceless is maintenance service agreements. So we work with Hawk, and being able to call them and having them come to the field and help maintain a lot of these analyzers and sensors has been a huge benefit, and we have a great relationship with them. So if you have the opportunity to set one up, we highly recommend it. To bring back into the conversation the manifolds, so we did build this in the field and it ended up working really well. So we have a TOC analyzer that can really only analyze one stream at a time. And this manifold allows us in combo with our SCADA control system, can open and close different valves to pull samples from different parts in the process. So overall key takeaways, make sure you can have a way to test for water quality, but prior to deployment, that you can kind of establish a plan for making sure the water quality is sufficient for what you're trying to do. A contingency plan, especially if you're piloting away from home, dedicated point of contact, and working with the wastewater plant or wherever you're deploying is really critical. And keeping in mind 24/7 operation that requires a lot of planning and coordination. And our last note here, in the upper right-hand corner, you can see a photo of our trailer without a wheel. This particular issue is just a matter of years of adding and changing and building out a trailer, and making sure the trailer can handle the new weight of the systems you're carrying. So that is some of our key takeaways, and we'd love to have some questions after our next presentation.
Bring a spare tire. Nice, Lisa. Okay, thanks very much. All right, our final group before we go to Q&A is the Trevi team. And we've got Jackson and Haley and the team in Rohnert Park, California. Welcome, guys. And tell us what you were up to.
Hi. Sorry, a little housekeeping here.
All right. Hi, guys. Good morning, everyone. My name is Junaid. I'm the Senior Mechanical Engineer with Trevi Systems. Today, I'll start by giving a high-level overview of our NAWI field trials, what we are trying to demonstrate, what systems we built, and how those systems were installed and operated at different sites. Jackson and Haley will dive deep into how they were run and what were the key learnings from this whole experience. So our main objective was to demonstrate a high water recovery across different inland water and brine compositions. We were targeting like near zero liquid discharge operation with greater than 95% overall recovery, while still maintaining good product water quality that the sites required. We also wanted to compare two different softening/desalting pathways, switchable solvent treatment and EDM, which is electrodialysis metathesis. So the pilot was not just about whether we could concentrate brine without scaling, but also about understanding which process pathway made the most sense under real-world site conditions. At a system level, the process included a pre-treatment in form of media filters, multimedia filter, cartridge filters, and UF. Then an upfront RO wherever we could install it and run it, until we can concentrate it further. And then either an EDM or a switchable solvent treatment train, after which we could do a final recovery of permeate using pressurized forward osmosis. So this slide shows our first version of the mobile pilot system, which was a 20-foot container. The EDM system, as you can see, is housed inside the 20-foot container, but the tank storage was arranged outside the container. We had about 8 to 9 tanks outside. One of the big design consideration was mobility. So we needed a system that could be transported to multiple sites, connected to different water sources, and adjusted depending on site's water chemistry and available utilities. The outside tank layout gave us flexibility to connect to various process streams. Inside the container, the subsystems were arranged to keep the core processes compact, protected, and easier to operate on field. So this slide shows from the same container, the switchable solvent system. The purpose of the system was to test a softening pathway before concentrating brine beyond conventional thermal ZLD. In practice, this meant integrating additional equipments like tanks, pumps, heat exchangers, instrumentation, and solvent handling components into field deployable skids. One important point is that field installation is never just plug and play. Each site required adjustments like hose routing, tank layout, sampling points, containments, utilities, and operating parameters all had to be adapted to the actual site conditions. So as a project developed, we also used a larger 40-foot container configuration. This allowed us to separate storage, controls, and process equipments more effectively. As you can see on the left screen, our 10 containers became 18, our 10 tanks became 18 tanks, and that's our tank container. And the right-hand side, it's like our membranes, all our membranes and all our equipments were on the right side. So from an installation standpoint, the system was designed to arrive as a mobile treatment platform. Once on site, the main task were positioning the containers, connecting power, connecting feed and discharge lines, setting up containment, and verifying that the site could support the operating conditions. So to summarize my section, we tested both EDM and switchable solvent pathways in our mobile containers, and we installed the system in such a way that it allowed us to move between sites, handle different water chemistries, and learn what it really takes to operate these technologies outside the lab. I'll now hand it over to Jackson, who will go deeper into site-specific results and the lessons learned.
Hi, I'm Jackson. I'm a process engineer at Trevi. And this slide is a general overview of how our approach for piloting at each of these sites. So we would start by analyzing the provided samples and data, whether that was from our own analytical equipment or prior customer data. Then we would run lab scale testing based on that information. We would model, plan, and build our treatment methods. Then we would get to site and we would have to verify our source samples because sometimes logistics or site restraints it might have changed our water source, or seasonal variations like harvest season might affect our water supply. Then we would update and adjust our treatment methods based on that information, run the treatment process, analyze that process's output samples, adjust the next treatment process parameters, and then repeat that cycle until we finish our treatment train. And then we would collect and analyze our final samples. These are the overviews of the 5 sites that we trialed at. In order, they were Pleasant Valley Pistachio, San Luis Obispo, California, Trinchero Family Estates, Cambria, California, and Windset Farms. Under each of the photos is a general description of the water source that we received, some brackish groundwater or RO reject. And there is the general TDS of what we were receiving, generally below 2000 ppm. Some site-specific issues, like some sites had high bicarbonates or high silica or high organics. What the end-use conditions were for each of the sites, and what our target versus our overall recoveries were for each of those sites as well. And a question might be, how did we choose each of these sites? We typically chose them by having these various water compositions, and as well as their varying end use conditions was a factor for us. We were also, trying to target potential customers. Showing the customer what you can do is a lot better than just telling them what you can do. We also were keeping in consideration key logistical factors, which Haley will expand upon later. And finally, like I mentioned before, site availability is also a factor. So again, I'm sorry,
Lisa before you, or Laura and Jim at the beginning?
no, sorry, I'm talking about like I just mentioned, we were talking. I'm so sorry. We Site conditions like harvest season. I'm sorry. That was a particular factor at Trinchero and Pleasant Valley Pistachio. And what were the outcomes of our pilot? We were able to achieve high recovery at 4 of the 5 sites, along with high permeate quality at those sites, generally between 200 to 300 ppm. And for those 4 sites, we were able to achieve concentrations of over 100,000. We were also able to demonstrate the benefits and limitations of both our switchable solvent and our EDM processes. One particular issue with the switchable solvent process is that waters with low scaling factors, it is not very beneficial for, as well as waters with antiscalants. It's something critical that we learned. And lastly, we showed that EDM was typically more effective for these inland water compositions that we were looking at, where switchable solvent might have more targeted applications that we're excited to explore in the future. And lastly, for me, what would we do differently? We would definitely run more lab scale tests with real water samples, so that we could anticipate the practical issues and operations better. This would have helped us particularly at a site like Trinchero. Um, and we would have more immediate chemical species feedback for things like silica and bicarbonates were also very critical for us. And now I will give it over to Haley for some advice.
Hi, everybody. I'm Haley, our PLC programmer and one of our field trial operators. This is the advice we have for any team doing field trials in the future. Some of the things I'm about to say sound like common sense, but simple common sense points are the easiest to miss when you've spent the bulk of your time on process and engineering level questions. So, before you go, identify key logistical challenges. When are you moving and how are you getting there? Who's going? What is the site's availability as far as schedule, space, power, and water hookups for product and wastewater? How and when will samples be sent to a lab and analyzed? Et cetera, et cetera. Honestly, no factor is too small to consider. We found it extremely helpful to set up direct communication with site personnel early. They know their water and their site better than anyone, and often provided valuable insights that allowed us to show up prepared. Also, allow plenty of time to debug and get to know your system before you leave your controlled environment, so that if something does go wrong, you don't waste time doubting the mechanics of your system. You rather spend time on the meat of your issue. VFD issues aren't groundbreaking. So perform a full factory acceptance test. Performing a full factory acceptance test will enable you to discover problems before they become larger down the line. Any debugging that isn't completed at home will cost you threefold in time and inconvenience in the field. So on the left here is a picture from the day that we dialed in our EDM system at the lab. So along the same lines, any person or tool that will give you insight into the status of your system and keep the process moving is valuable. Some useful tools for us were multimeters, Myron L, and targeted species test kits, like Jackson mentioned earlier. Water treatment is an interdisciplinary field. We found it helpful to have technicians on site who were cross-trained in all the different fields that we interact with. It's also important before you go to clearly define testing goals and methods. Success will be based on different parameters for different teams, but there must be at least one metric that indicates success. So while you're there, even with all that preparation, once you get there, eventually something will go wrong. Fittings break and equipment fails. Try to be flexible and brush up on your troubleshooting skills. The picture on the left here shows some of our unanticipated issue. So on the left, you can see significant gypsum scaling in our switchable solvent system, meaning our system worked, but catastrophically well. Middle photo shows one instance of chemical incompatibility with an O-ring, also within our switchable solvent system. The last is a photo of our pre-RO filters at Trinchero Winery, where pre-treatment unexpectedly took center stage over our downstream processes. Also, while you're there, environmental factors need to be considered. Beyond the heat, there were fires in Coalinga while we were trialing, which disrupted hotel stays and air quality. And the two photos to the right and the left show Trinchero muck and torrential rain in Cambria. All I'll say is that waterproof boots are a must. So also while you're there, take notes. It's much easier to write down what happened in the moment than to retroactively fact hunt. Along the same lines, make sure to work with your teammates. One of our biggest strengths as a company is the collective knowledge of our team. I'm sure it's the same for all of you. Don't be afraid to ask questions when you don't know something, or think out loud so you can bounce ideas off each other. So after you return, check in with your team. What went well, what needs work, and how can you bring the lessons learned to the next site or project? So we want to say a special thanks to everyone at the NAWI team. This grant gave us a framework and helped to kick our novel technologies out of the lab. Thank you to everyone at all the sites we visited. Thanks to Clark and Patrick at GWI. And finally, we want to encourage anyone in a position to apply for a grant with NAWI to do it. Field trialing in particular was a great experience for us. We learned so much and we appreciate the opportunity. Thank you.
Thank you.
Thank you.
You are very welcome, everybody. Thank you so much for these three presentations. I know we've had a lot of questions come through here, but I want to actually give each of the pilot teams an opportunity to ask any questions of each other because I sense some commonalities here. And maybe as you were listening to a few others, maybe Haley, when you're listening to Lisa's talk, you're like, oh yeah. So I don't know. Any of you have any questions? Raise your hand, and you can ask the question of any other team member before we pull into to general questions. So, any thoughts or questions? Yeah, you guys unmute and go ahead.
I think I had a question for Lisa. You mentioned that you used cloth filters, and I just wanted to know, like, how did that perform, and did you consider using a UF instead of a cloth filter for that?
Yeah, so the cloth filter, we were dealing with pretty high solids, so we weren't necessarily considering a UF at that point. We
It
have
was
a
pretty chunky, right? Yeah.
Yeah, it was pretty thick solids. I probably have another photo I could pull up and share
Yeah.
or share with you later. But we wanted something a little bit more to handle like the thicker solids versus if we were to bring in a UF, it would probably clog it way faster and require way too much hands-on maintenance. Whereas this cloth filter, I could pull up a picture if it's helpful, but it had like a shop vac attached to it. So it went through a backwash cycle. The shop vac removed the thicker solids that clogged
Sucked
up.
it right off. Yeah.
Sucked it off.
Yeah.
So it was because you chose it because it had big particle size. That's why you.
Yeah, it was like thicker solids. But we did have a inside the trailer after the cloth media filter, we do have a 80 micron amide filter that does a self backwash. And then further down the treatment train, we do have a ultrafiltration unit. But yeah, for those more like heavier solids, we wanted something a little more robust.
Yeah, but Lisa, this was an example. I mean, wasn't that equipment something that you guys rushed out from Colorado? Because
Yeah.
you kind of got there, and again, below the very terse bullet points lies a lot of hours, right? And
Yeah.
so, Lisa, you may want to talk a little bit more about what are the consequences. I mean, one of the issues you faced in Redwood City, California, was Zai having to drive. Once you got there and you realized that the water condition wasn't nearly what you all were expecting, Zahi was left, jumping in the truck and bringing equipment across from Colorado to California. So it does say, friends, that proximity is next to godliness. If you can do a pilot and you have two choices, one that's 1,000 miles away and one that's 100 is a pretty easy choice. But Lisa, tell us a little bit, maybe a little more color about when you got there. When did you all realize that, like, oh crap, literally, this water is not nearly what we were prepared for?
Right. So I think our biggest issue was the plant we arrived at didn't have the infrastructure to remove ammonia from their effluent. So while their tertiary effluent wasn't crazy high in solids, it was the secondary treatment pilot that we brought in or that was brought in to remove the ammonia that formed all these solids and had poor solids handling. So when we were trying to receive the effluent from the secondary treatment pilot, that was the solids there were really overwhelming our systems. And we did bring in a secondary pre-filter, like I mentioned, but within maybe a few weeks, it blew out the motor because it couldn't self backwash enough. The filter on that amide got clogged. So then our option was, what can we bring in to handle this thicker level of solids since this secondary treatment pilot, we didn't have an obvious solution for that system either.
Yeah.
And feel free to chime in, Zahi, if I'm missing key components here. But yeah, the cloth media filter, while it worked really well at our Mines Park pilot, which we mentioned previously, handling raw sewage, it's not a small unit, so it was a lot cheaper for Zahi to drive it out versus trying to like ship that. I don't know how heavy it weighed.
I think
So
the more important thing is that you have it, on hand and you can very quickly respond and bring things to the field. How exactly you bring them to the field is not important. I think, we are, unfortunately, we learned very quickly that we have problem with the water quality. And I think that the big lesson is that if you are bringing another pilot to solve a problem, you have to really make sure that that pilot is going to work. And in our case, this BDP system, later on, after a few months that, we tried and we tried and tried, it's a biological system. We had to start it from scratch. It took us time to realize that it's not going to perform the way that we need it to perform in order to feed the DPR trailer with the right water. So I think that's I wanted to ask. I think Laura said, automate when possible. I totally agree. I found that actually in the trailer, wherever we can keep things not automated, like sump pumps or the pre-filter that Lisa is talking about, it's like just don't connect it to the SCADA. It does every 2 hours backwash. Just leave it aside. It's like some more comments from you.
For sure. In our case specifically, for example, we had pH control almost manual, and it made it really complicated for us to adjust our level of aluminum going into the seawater unit. So that one particularly was something that first could have been easily done. Second, would have actually not been very expensive. And third, would have saved a lot of time for the operator. So these are things that you only really learned after several months of operations. And then the team is like, wait a minute, we could have done all these things differently. So when possible, perhaps also has to be caveat as like, is it reasonable for you to do it? Is it gonna bring a benefit? Because in our case, it would have brought a lot of benefit, but I know I can understand from your case, perhaps was not the solution. So I guess you kind of have to weigh those two options and understand where it's actually feasible. And if you can do it, I think it's best to do it early on so you can save your team some hours.
So,
Yeah,
so I want to comment especially on something that Travi people said about taking notes. No doubt, taking notes, is super important. And when you have good SCADA system to collect notes, or data, that's super important at the right frequency of collecting data. Um, a tip that I want to give to everybody, because we developed the control system internally, and changed it so many times. In the last year, we implemented in all our pilots a digital notebook or a digital logbook, which means you're doing something on the SCADA system. There's a box. You type what you have done, and when you click enter, it gives it a timestamp. It creates a parallel text file, and whoever will go to deal with the data in the future, which will be engineers, statistician, whatever, and say, oh, something weird happened here. They can go to the text file and say, this is what happened. It reduces a lot of headache, much easier to manage a physical notebook that gets lost. And we found it
I think
great.
it's a huge, great piece of advice, Sahi. Absolutely huge. I just want to remind everybody, we are going long here. We are just getting cooking on the conversation. We're just having the teams talk to each other. So everybody who's listening, if you need to drop off, I apologize. But for those of you who want to stay on, I will give audience members an opportunity to ask questions. But I still want to keep cooking with the teams themselves. And Zahi, I think the other element I would say is that as one of the places where I see, the kind of pilots that are starting from a research standpoint or from a research university have an approach to documentation, an approach to experimentation. And industry, you're often like, oh, I just got to get it done, got to get it done. But this is where the industry people sometimes need to understand that being a little bit anal and methodical in documentation, in the end of the day, saves you a huge amount. But it can be very easy to kind of discount in the hustle and bustle of getting something done, especially given the time urgency that a lot of these pilots are under. So I appreciate that.
I'm not an expert, but everybody has a SCADA system, and I don't think that incorporating a digital logbook to a SCADA system, that has a clock and it collects data anyway,
Yeah.
that's something very easy to implement.
Yeah, well, Zai, you said one thing about, choosing between an quote unquote industrial or experimental SCADA system. Are you referring to like, say, an Allen Bradley PLC versus essentially a LabVIEW based, kind of a PC based system? What's the
Yeah,
distinction you're
yeah.
drawing
So,
there?
so, so maybe I didn't use the right technical terms, but you're absolutely right. We built most of our pilot system with LabVIEW as the language platform, the programming, and we're using a local company called LabJack for all the hardware. And we found over the years that LabVIEW is a great sort of academic tool, very flexible. Um, we built the LSRO pilot with Ellen Bradley. And the truth is also that our SBMBR pilot system was also built with Ellen Bradley. Ellen Bradley is the top of the line. It's the best, but it's best for a plant that just needs to work and
Yeah, and in
not
a
change
very kind of
information.
specific operational
Yeah,
box. Yeah.
you can move things a little bit around, but it just works. We found that with LabVIEW, we can do much more sensitive things. We can do calibration curves with 6 points. We can incorporate LabVIEW with Python. We can do a lot of things that are just easy with this. So again, it's maybe people that understand the other platform better, will not agree. But for us, it works well.
Good. Thank you for that. I want to invite, pilot team members, any other questions you have. I want to get back to this issue of like, I don't think I've ever heard in the history of every pilot I've ever encountered that somebody said, "Oh, we spent too much time analyzing the source water before we got there. Like, we shouldn't have done all that. We should have survived." In every case, I have heard major surprises, and I think the one thing that Lisa and Zahi mentioned was that everybody tends to think about like, oh, it's just water quality. Like, get me averages, get me ranges, I'm set. But it's also water supply and pressure. And I thought that was a really good point, Lisa, that you raised with the bladder tank. That you basically, in some situations, you may not be able to control exactly when that water arrives or how much pressure when it arrives, et cetera, et cetera. Don't think you're going to a pilot site with like a beer keg and a spigot, and I can just get the water whenever I want. So this is where simple things like, well, maybe I have a storage and equalization tank ahead of time. The dilemma there is you're now introducing a new unit process that inevitably involves settling. And so you kind of have these issues of like, well, what am I giving up in terms of the clarity of the test versus what am I gaining in terms of the stability of the project? And so those are really important things. Zahi.
And on top of that, something that I just realized later that we forgot to include in our presentation, the size of your SCADA systems. If you are building your own or ordering your own, whatever you need for the initial design, just double it. Because when you do expansion and then you realize, oh shoot, I now missing more, analog outputs, and I cannot put another valve or another pump. Uh,
Trevi, you guys are squirming, aren't you? Oh,
yeah,
God.
this
Yeah.
is so important. And every time that we build a system, we say, yeah, now we're doubling it. And again, you
Yeah.
find that you're missing here and there, and then you can expand, but the expansion are always more complicated,
Yeah.
cost more time. you better off, from the onset with the larger SCADA system.
Yeah, yeah. Any other questions from you all? I'm going to pivot to taking some questions and inviting some people from the field. One thing I did want to ask you is early on in the NAWI pilot process, we had thought that you all would use water tap and do a kind of a process model of your system and kind of inform the design of the system with water tap. I don't think that happened. I think I know why we didn't end up going that way, but maybe first of all, Trevi, maybe that's not a Haley or Jackson question, but like, have you guys cracked open WaterTap? Where did you see WaterTap? Did WaterTap play any role in the design or operation of the system?
Maybe that's a question for Michael and John.
Okay,
But
convenient,
I
not present. Michael Green, you are not here. All right.
but I think I have heard about the water tap infrastructure, and we are going to use it for all our future projects that are coming up.
There you go.
John
Yeah,
is like heavily interested in like using that
yeah,
resource.
yeah,
Yeah.
yeah. So Laura, sorry, Zahi, you first.
So I think it takes time to initiate the process with water tap. Um, we, at certain point, unrelated to our project, because one of the earlier project on the direct potable reuse system was developing digital twin, um, in optimization on the fly for the system. And that's, again, I'm saying system, but these are, optimizing 6 different processes at the same time in a trailer.
Yeah,
And we took one approach together with Oak Ridge National Lab. We started working with the water tap team on actually on LSRRO when we
that's right.
realized that, it looks like a simple process, but it's complicated. And I think that the water tap team solved for us amazing problems with the modeling, and it took us time to appreciate what a strong tool it is. And only now we're going into the DPR trailer and say, okay, now we're going to implement similar things in the DPR trailer with water tap because that will connect us to the digital twin, that will really connect us to the optimization on the fly, that will connect us to, design of better things, and that will connect us to techno-economic analysis.
Fair enough.
So it takes time.
Yeah, yeah, good. Um, I see a bunch of questions. One of the other ultimate goals here, of course, we not just demonstrate efficacy and water recovery, but we eventually want to arrive at a rigorous techno-economic analysis to try to really say, okay, at full scale, what are our cost implications for, dollars per cubic meter, et cetera, for this treatment given this initial water type. So I'll start with Trevi. Have you done that analysis? I mean, partly you were comparing two processes, switchable solvent and EDM, and looks like EDM's a little bit more, kind of generalizable for you all. But where are you all with the techno-economic analysis of the levelized cost of water treatment? Do you have that number for all 5 of those water types? Granted, some of that's secret, but like, where are you with getting down to the brass tacks of the nickels and pennies of that?
Peter, let me answer that from total water.
In Russia's the
Yeah,
project developer.
yeah. So we only have the levelized cost for 2 of the sites so far
Yeah,
because we've prepared quotes for 2 of the sites. And you obviously
interesting.
can't have a levelized cost unless you know what the CapEx is going to be along with the
Right,
OpEx.
right.
We did with the EDM, we did hit our target for the pilot. We were under $5 a cubic meter. That's a levelized cost of CapEx plus OpEx.
Uh-huh.
And I would also point out that that's with California's extraordinarily high electrical rates. Um,
Fair enough.
and uh, and that's per cubic meter. And what was particularly interesting is the actual OpEx costs were basically around a penny a gallon, so
Mhm.
about 250 a cubic meter, which
Okay.
is really extraordinary when you consider a multiple of our sites hauling their brine is costing them 22 to 25 cents a gallon.
Yeah.
So we were looking at an operating cost of a penny a gallon, which is just extraordinarily
Yeah.
advantageous to these sites.
Absolutely. Yeah. So Clark, I think you bring up a really great point, and maybe this is another kind of meta point. Um, One of the things that made the Trevi project so exciting was not just that you were visiting sites, but you were also shopping for conversion to full scale
Yes.
projects. And Clark, you've gotten, at least so far, you're moving ahead with two, which is really exciting. So I would also say
Mm.
for anybody listening to this in the future, as you think about the NAWI pilot and the NAWI funding, we are especially excited when you're doing this for the prospect of actually converting a pilot into a full scale opportunity. Not the least of which is that then, with that project development, we get to resolve the full capital costs
Yeah.
associated with these innovative water treatment systems. So, Clark, I give you extra credit for having that endpoint in mind and motivating this project. I don't know if Zahi or Lisa, um, DPR is being approached very differently state by state. California has its canonical thou shalt, kind of treatment train. Texas, it's like, I guess, whatever you can strain through your teeth is probably good enough. So, where do you guys see the value of technoeconomic and sort of cost analysis in the DPR research that you're doing?
Wow, this is a tough question. Yeah, DPR is a tricky business, and I'm sure that it will continue to be controversial and with different opinions, in different states. They say about academics, two professors, three opinions. And I think the same thing applies to states. Um, I think that it will come with drought. Every time
Mm.
that the knife is getting close, people make decisions that initially hard to make these decisions, and the publicans say, "Oh, I won't have water, so I have to make the decision." And you have to, it takes time to develop it. And we have seen what happened in Perth and in other places in Australia, that suddenly when the sky opened and it started
Yes,
raining,
literally, right when they
why
commissioned
why
their
did we
RO
invent
plants.
why
Right.
did we invent in RO,
Yeah.
invested in RO, sorry. But I think a trailer, the value of a trailer like that have all this flexibility and the ability very quickly to hook up to your water source and test it for a month or two or three to see how under different conditions water quality changes, and to fit the right processes, that gives stakeholders some better feel for, are we risking something? Can we do it? Again, I think our frustration in California was that first, when we did the preparation, and Lisa mentioned the contingency plan, we talked to other plans to see, if something happened,
We can't work here. Yeah. Could we go somewhere
we need
else?
to
Yeah.
move quickly. The first plan that we talked to didn't work out for different reasons, and I will not open the reasons here. Just towards the end, when we say, okay, this is a waste of taxpayer money, it's like we shouldn't be there. We need to continue the research, and eventually we brought the trailer back to Colorado to continue the research. We tried another plant close to Redwood City. Um, Other sets of problem why we cannot quickly incorporate or integrate our system into there. I think that's a loss. I think that at the end of the day, to hook up, we built a trailer like that, and I think everybody that builds trailers and
Sure.
systems, they make the connections very simple. It's just give me the
Okay.
water, give me give me power, give me where to waste the water,
I used the wrong
and
number.
just I don't need anything else from you. So everybody need to be more flexible.
I was almost thinking, Zahi, and again, I know we're coming up on our close end of time, but I kind of wonder about the following. Like, you're going to go to a site. Yes, you've met with them. Yes, you've had Zoom calls. You maybe even visited the site. but I kind of feel like no plan survives first contact with the enemy, that joke from the Army. And similarly, I'm almost wondering if pilot teams should consider mobilizing a subset of the unit processes, maybe just one or two, and just do one thing there, and then kind of like work out all the kinks, et cetera, before the full package arrives. I don't know. You rolled your eyes, Zahid.
Yeah, it's like, it's like like if it depends. If it was just RO, yes, I can bring a small pilot and test it. Um, how do I bring a subset of direct potable reuse
Well,
train?
maybe you just bring one or two unit processes and just do those two steps only. I don't know.
That's an option. I think maybe a better option is to bring the site to where you're operating now. Say, hey,
So, like
here's,
what? Bring me three totes. I want
no,
1,500 gallons of
bring
water.
the people from Silicon Valley Clean Water to Sasplat Renew in Colorado to talk to us to see how it operates there.
Uh,
Talk to the administrators at the wastewater treatment plant. Ask them all the question of, what does it take to operate something like that in your backyard?
yeah.
Um, because at the end of the day, the places where and we have now many places that we've been, even Sasplat Renew, which is the third time that we are there now, fourth time that we're there. Every time these are different people because people moved
Yeah.
around. And
Everybody
so
shifts.
now it's like, yeah, the site, mechanically, we just connect and we operate, but you're dealing with different people. It's the enthusiasm of the people. If you have enthusiasm of, why we're doing it, here's also our questions, the research questions, not, and again, in our case, we are academics, so we, sometimes bring from home our questions, but you want a location that have their own question and they push you and they operate with you and they ask the tough questions, then you have success.
Yeah, that's a really good point. Um, All right, everybody, thank you all so much for spending time with us today. And I would also say you all are available to talk to other pilot teams. So please, for those of you considering working on a future NAWI project, reach out to this community of experienced piloteers, and they can give you lots of good practical advice on moving forward. I want to wrap up and just kind of say one final thing and give Jim and Laura an opportunity to talk a little bit more because we're talking a lot about sites and the quality and stability of the water. And so, of these three pilots that we learned about today, I think Jim and Laura experienced possibly the best environment because the Water Quality Improvement Center is designed to be a piloting facility where the spigots of RO concentrate are already very well conditioned, et cetera. So, and you had some extraordinary engineering help. So, Jim and Laura, just maybe some final comments about what you saw in that facility. And by the way, they'd be interested in hosting more pilots, people. So don't be afraid to reach out to them. But Laura and Jim, to finally wrap up and tell us a little bit about what you got in terms of support and what you saw in terms of what worked in that facility.
Yeah, I'll start. Laura can weigh in. But I mean, I've been familiar with the Water Quality Improvement Center because I followed the salting plant for many years. And I knew their capabilities. And so to me, when it came time to find a site, that site made sense to me to get access to the source waters. But more importantly, as we actually went through and conducted the pilot testing, we realized how much in-kind service they were providing. So we couldn't take credit for that in-kind because it's a federal agency, the way now we set up the contract. But we got over $100,000 in in-kind contribution from them in terms of engineering and operational support, also equipment they provided. And that really, without that, I think we would have had a difficult time achieving our goals.
Yeah.
But the fact that their staff could build anything we wanted them to build with a smile on their face and get it done quickly and deal with all the operational issues we threw at them, just tremendous capability on their part to do that.
Yeah. I see that glint in your eye, Haley. Yes, there is that promised land. It does exist. All right, everybody. Thank you guys so much. Laura, anything to add there?
No, I think that was something to definitely, the summary of it is check them out. If
Yeah.
you want to talk about our experience there, feel free to reach out. It definitely was very positive, and I encourage everybody to kind of think of them as an option in the future.
Great. All right, everybody, thank you again so much. And honestly, three pilot teams, thank you so much for the hard work you have done, the way that you have advanced our field of advanced water treatment. And we hope that we can keep working with you in future projects. And everybody from all of us here at NAWI, thank you again. And everybody, keep pushing the frontier because water is a precious thing and it's nothing you want to use just once. All right, everybody,
Yeah.
take
Thank you,
care. Have a good day.
everybody. Bye bye.
Thanks, Peter.
Bye-bye.
Thank you.